The main purpose of this lab is to understand the behavior of these elements and to compare our theoretical predictions with results from the simulated measurements. To analyze these circuits, we use three key principles along with these other ones. The node rule states that the current entering a node equals the current leaving it due to the conservation of charge. The loop rule states that the sum of all electric potential differences around a circuit loop is zero, and Ohm's law states that the current through a conductor is proportional to the voltage across it, with the formula delta V equals IR. We're also going to be linearizing some data and using conservation of energy and current, which is reflected in the loop and node rule. And you have to know the key components of a circuit: resistors, capacitor, battery, and we're going to use ammeters and voltmeters for the measurement. In this lab, the system is the circuit itself, including all the circuit elements. The surroundings include everything external, like the simulation environment and measurement devices. Our initial conditions are that we set up a circuit following the diagram for the last slide. We set the batteries to 1.5 volts, and we connected the ammeters so that the conventional current flows into the positive terminal. We labeled them as ammeter 1 and 2. We connected the two batteries and recorded the ammeters readings as L1 and L2. Then we reversed the connections of one of the ammeters. We predicted that the current would remain the same throughout the circuit based on the node rule. Some initial conditions were that we said that the resistance of the wires and the ammeter is negligible. We also assume that the current is consistent throughout the series circuit. Some findings we had were that when connection was reversed, the reading was the same magnitude but different direction, and the current through each resistor has to be the same due to the node rule. We used a voltmeter to measure the potential differences at different points in the circuit, and here are our findings. And the loop rule tells us that the sum of all potential differences is zero, which is reflected. Using Ohm's law, we calculated the resistance of each circuit element, assuming zero voltage drop across wires and ideal ammeters. Small discrepancies with simulation results were due to rounding errors in the calculations. What happens to the current when the voltmeter is replaced with an ammeter parallel with a 100 ohm resistor? Current reading will increase to 0.06 amps because the current is split at the nodes, so a portion of the current will experience resistance. Resistance and current have an inverse relationship. In this setup, we built two RC circuits and resistors, and we measured the time it took for the capacitor to charge and discharge. With the 10 ohm bulb, it took about 13 seconds to charge and about 13 seconds to discharge. And with the 20 ohm, it took about 28 seconds and 26 seconds to discharge. Here's the graph for circuit 2. We linearized it, and we found the slope and the RC, which corresponds to 8.95 seconds. And the theoretical resistance capacitance is 30 times 0.2, which is about 6 seconds, so we're about 3 seconds off. In circuit 3, we observed the voltage across a capacitor in a discharging RC circuit. As expected, the voltage dropped exponentially, consistent with the behavior of capacitors in such circuits. Here is a picture of our circuit. Some possible sources of error were human error and simulation accuracy. We assumed that the resistance of the wires and ammeter were negligible, but of course that's not the case, which would impact the results. There may have been errors in the measurements using the multimeter, and errors could have occurred during the setup, and we filmed the circuit on our phone to record the time, which could have been inaccurate. Additional questions. So what if the lab was in real life with an actual ammeter? We did use a real ammeter. This lab is a little outdated, but we did use that. What if you were doing this lab in real life with a real battery to charge a real capacitor? Blah blah blah. How quickly would our ideal model predict the capacitor to reach full charge? Capacitor in the simulation charged instantly because there was no resistance in the wires, but real wires have a slight resistance, so it would take longer to charge. This ammeter also has some resistance in real life, so that explains